has been forcing their formation. So I will base my talk on these 4 papers, of which one of them is made by Saija Salminen, my PhD student who just finished her PhD 1 year ago. And the rest are a bit more older, but still really cool ones. So I will guide you through this. Just starting from the Finnish varve records and how they normally are formed. So we are in mostly in boreal climate zone, and we have pronounced difference between winter and summer conditions. Winters are usually described with a lot of snow, and summer are still quite warm and comfortable. We lack carbonaceous rocks at our catchment, but most of the bedrock is formed by crystalline um, rock types formed already more than 2,000 million years ago. Typically found varve types are clastic biogenic varves, and sometimes some of the varve records just lack the clastic lamination, so then it's just biogenic varve type, but those are quite few compared to how many clastic biogenic varve records are found from Finland. So everything starts in spring when the snow is melting and it is causing a spring flood and strong runoff and catchment erosion, and we have depositions of minerogenic, detrital minerogenic matter, and ideally they sometimes show graded bedding even, but usually it's not very clearly visible anyway. Then comes the summer, and we get accumulation of organic, biogenic matter, and then comes another winter and another spring flood layer will be formed on spring. Those records that simply lack the clastic laminae are just biogenic, and how we can distinguish between the biogenic layers are the difference between what is deposited during summertime. There is, if you look at the microscope, the bright layer is growing season and it is full of life. There is a lot of diatoms and pollen frustules and chrysophyte cysts. And then underneath the ice during winter, the amorphous organic, really thin and dark layer is formed. And in that layer, it's really difficult to see any clear structures, but it is just basically black. And these layers you can also see, or these sub layers of biogenic laminae you can also see in many classic biogenic varve types, but it is not, because the thickness of this amorphous winter layer is very thin. It can be like 0.1 millimeters, so it's quite, it helps to distinguish between the varves, but it is difficult to measure the thickness of this particular laminae. So these are the varve records I'm going to talk about today, and there is of course many other records published from Finland, like Antti Ojala's work from Lake Nautajärvi, but I have not worked there, so I just included all the lakes I've been involved somehow. And we have 2 meteorological stations that we have mainly used for these studies, and one is right next to the Lake Kevojärvi, so it is just on the shore, which is really ideal situation. And the second meteorological data set is collected from the city of Kuopio. So it is less than 100 kilometers away from all the lakes, but just keep this in mind when we are looking at the correlations between meteorological data and our Varve records, because this distance can cause a slight bias in the dataset. Anyway, this shows that we have a lot of precipitation during summer time, and when we also have a peak temperatures. And in the southern part of Finland, there is the precipitation occurs more evenly than in the northern part of Finland. And here are the stars of the day. So some pictures of the laminations of these lakes. And the left one is Lake Kalliokourujärvi, and that is the one and only biogenic varve record that we are studying today. And the rest of the lakes are clastic biogenic varve types, and same, but still slightly different. Lake Lehmilampi and Lake Linnalampi, far right, are from 10 sections, while the middle one, Lake Kuninkaisenlampi, is from epoxy block, so that causes a bit color difference, but basically the minerogenic, the clastic lamina is bright, consisting on clays and silts, and the organic layer is more black, and you can see, well, not very clearly from these pictures, but you can see all kinds of nodules and life forms incorporated in the biogenic laminae. So we have quite nice correlation between the meteorological data sets with winter precipitation and the proxies describing the clastic material deposition though. So we have these 3 lakes are analyzed using image analysis technique. And that's why we have light sums on the y-axis, but it is representative to the amount of accumulated minerogenic material. We have really high correlations for winter precipitation, and that is, well, it is not surprise, it is more expected, because we expect the more snow, the more intense spring flood, and the more catchment erosion we get, the more minerogenic material is deposited on the lake bottom. So it's not very new, but it is very valid hypothesis, and it makes things very easy. So this is some unpublished data from Lake Kevojärvi, where we analyzed also the micro-XRF, and this is the titanium. I'm not sure if you can see my mouse, hopefully, but so the titanium counts. Titanium is incorporated only in minerogenic material. It cannot be formed by biogenic processes, and that's why we use it as a proxy for minerogenic input. And it follows so nicely the North Atlantic Oscillation Index that in Finland, positive North Atlantic oscillation usually yields more stronger westerly winds that brings the humidity to the Finland, and we still have so cold winters that even the positive now situation characterized by more mild and humid winter, it will be anyway causing increased snowfall in in the central and northern part of Finland. And I just, I like this curve so much, but I just had to draw it like a couple of times to be sure that I am not drawing the same data set over and over again, because I just think it looked so much similar. So yes, it makes things very easy. This is very straightforward, and we can just use it to record atmospheric circulation patterns far back in time, as far as we can reach with our data system. But then we did the same analysis for the next set of lakes, and all of them showed negative correlations, and we really struggled to understand this system. And again, we had to do things twice to be sure we did not do any mistakes, but the correlation just stayed. They are quite quite strong correlations, around 0.5, 0.6, but still they are negative. So what could explain that? I think there is two facts behind it, and they probably equally strongly influencing this system. So all of these three lakes are located in the central Finland area, and this is the image left is from Uvo paper, and he investigated the variance of winter precipitation that was explained by North Atlantic oscillation from modern meteorological data. And we can just see that the central Finland area, for some reason, do not or is not sensitive for North Atlantic oscillation at all. The second thing could be really in the catchment. So like we always say that varves are formed related to the catchment characteristics and climate. And here I think it is really true that the catchment has a strong influence on this lake system. So these three lakes are located in the area of fine-grained tills. These formations were formed at the interlobate area, like dead ice sheet zone, that is just like a cone-shaped area in central Finland. And these fine-grained tills are really sensitive for ground frost, so much more sensitive than sandy moraines or coarse moraines are. And what we could find out is that those minerogenic layers followed the solar activity. So in the picture below, you can see beryllium-10 and carbon-14, and the peaks are related to the low solar activity, and they occur at titanium peaks. And we believe that this is related to the situation caused by or enabled by a low solar activity situation that promotes an enhanced atmospheric blocking situation over the northern part of Europe here. And it is related to the high pressure, cold winters and dry winters. And here you can see the yellow dot is our lake, Lake Koninkaisenlampi in central Finland. And when it's dry, when there is not that much snow, which insulates the ground from the cold air temperatures, the ground frost can go deeper and can develop stronger. So I think it is both the area that in fact enables the sensitiveness to this winter drought situation, but also the catchment that enables the high pressure to cause more significant ground frost. And then at the time of spring floods, when we have the enhanced surface runoff, but due to ground frost, we have less water infiltration onto the frozen soil, and that's why we've got more pronounced erosion at the time. How to really test if this ground frost is significant or not? And I was really lucky to just be winding things in the right place, and I met Markus Johansson, who is really really capable in building all kind of equipment, and he built this automatic sediment trap. So the trap itself, he put infrared lights sensors within the sediment trap tube, and detectors that combined together. The sediment trap could just scan itself every hour, and we could have really ultra high resolution data from the sediment accumulation in a lake. And this lake is just right next to Kuopio meteorological monitoring station. And we got the hourly data, but here I present the daily data. So the blue bars denotes 4 milliliters of accumulated sediment per day. Of course, we do not know what exactly accumulates because we did not have a chance to hourly analyze the data, but we just measured the volume of accumulating sediments. And at the same time, there was a construction work going on, or it started at the end of our monitoring period. So it is marked here with the green line, and the blue line states for the ice cover. Red line is for snow cover. And well, this is mean depth of ground frost. This is the blue line here below is the actual depth of observed ground frost at the time. So we learned that what is known already, that the sedimentation is seized during the winter underneath the ice cover and when the ground is covered by snow and frost. But we could also see at the time when the frost start to go deeper and develop, we have really no sedimentation at all. When the frost starts to melt, we start to have these sedimentation peaks. And on the half April, when the fastest melting of snow occurred, we have the highest peak of erosion as well. What we also observed is that significant amount of the annual sediment deposition actually occurs during the growing season, which made us wonder whether we should focus more on what is going on during summer time. What we could think of is again the precipitation. So we believe that much of the material is washed to the lake during the precipitation, and now the red line is the daily precipitation in millimeters, and we can see that after can you see my mouse? I hope so. After each hard rain events, so at the time or just right after, we have increased deposition, and underneath the ice the precipitation does not really influence that much. But when the snow starts to melt, it has a direct impact on the accumulation. So we started to focus on the growing season laminae, and we were thinking if the biogenic lamina thickness could actually work as a proxy for summer conditions or open water season conditions. We chose 5 lakes from different catchment types, so the 3 ones from this interlobate area with fine-grained tills, and then Lehmilampi and Kalliokourujärvi with more coarse moraines on their catchments. Our working hypothesis was that the growing season precipitation must play an important role on the lamina thicknesses, but we mostly decided to analyze the mean annual growing season temperature. So when the daily temperature exceeds 5 degrees, that is from April to September, and mean annual open water precipitation. So that is precipitation that occurs between April and November. And this was our working hypothesis. So we acknowledge that the biogenic laminae are more prone to be influenced by more diverse phenomena than clastic laminae tends to be. And so like the higher temperature can promote autochthonous production, but also it can influence on the degradation rate, and it can also influence in oxygen availability through the stratification period, the intensity and the length of growing season stratification. We think that precipitation can influence the biogenic lamina through the transport of terrigenous biogenic material, but it could also influence on nutrient availability due to increased soil leaching of nutrients, and hence it can, with a certain delay, it can promote autochthonous production as well. And then we have the oxygen availability for the degradation or preservation of the biogenic lamina or biogenic material in the lake. So here is what we found out, and it was again a bit surprising with the correlations, because we had a strong positive correlations to temperatures and quite diverse correlations to precipitation. So here the black curves reflect the biogenic lamina thickness in millimeters in each of the lakes, and the red or the orange line is the temperature, mean growing season temperature from the Kuopio meteorological station, and the blue line is the precipitation, open water season precipitation throughout the 100-year record, also from Kuopio station. So you can see it's all the same structure because of the same station is used. What could explain, what we think could explain the positive and quite strong correlations between the growing season temperature and the biogenic lamina thickness is probably through the autochthonous production. And while we have no significant correlations for long terms for the Lake Kalliokourujärvi, the uppermost ones, we do have significant and quite good correlations from the other lakes. The other lakes, all of them are eutrophic lakes. Some of them just like naturally eutrophic, and some of them eutrophied. And we think that the temperatures promoting the autochthonous production are related to the nutrient availability. So there is always some energy left for the biogenic stuff to start and keep on growing when the conditions are ideal. Whereas in the oligomesotrophic Lake Kalliokourujärvi, the autochthonous production likely very rapidly is ceased because of nutrient availability. And we tested the correlations for the short periods or shorter periods to see if we can find significant correlations with a shortened period. And we did find first positive correlations for the first 40 years. And then since year 1935, we've got negative correlations. And of course, we cannot really be sure, but it can be because the same time interval is showing quite high summer temperatures compared to the time before. So it can maybe be so that the enhanced temperatures and the faster degradation of the biogenic material already in the water column just overrides the production that is anyway limited in oligomesotrophic lake. What could then explain the strange correlations between the precipitation and the biogenic lamina? We have again 3 lakes with positive correlation, and Lake Lehmilampi is showing really nice similar patterns with the curve, and the correlation is high and significant. And this might be because it is a headwater lake and not really influenced by the change of lakes in the upper catchment. So that could maybe explain why the Lake Lehmilampi signal is so beautifully correlated to the precipitation. This is what we expected that we will see. But the rest of the lakes are not that clear, and the correlations were indeed higher for the temperature. It could, of course, be that the intense land use by anthropogenic activities, there was forest clearance occurring in the Lake Kantele at 1955 and in Lake Kuninkaisenlampi since 1945. And in Linnalampi there was a forest clearance, rather short period of time, but it occurs exactly here at the same time when we have a high peak in biogenic lamina. So maybe human actions at the catchment really changed this pattern. We have, for the short time intervals, we've tested for Lake Kalliojärvi and Lake Kantele. These both 2 lakes did not have significant correlations for the long-term data set. We tried to seek if we can find anything for the shorter intervals. And we found negative correlation for the first period of the Lake Kallio-Kourujärvi turning to positive strong correlation after the 70s. And it can well be that this is related to the peatland drainage that started 1973, because the change seemed to occur at just coincidentally at the same time. In Lake Kantele, it has negative correlation as well, and this is what we really struggle to explain. It remains a mystery so far. It could be maybe that the enhanced river discharge could cause more turbulent waters and hence more oxygen on the bottom to increase the degradation of organic matter. But again, this lake had correlation of 0.74 against the temperature. So for maybe some reason, it is just more sensitive for temperature than precipitation. So the question, can we use biogenic lamina thickness to reconstruct past changes in growing season conditions? Is definitely maybe. Understanding the chemical cycles within the varve composition likely helps. And this is just an example what would be the next step. So to scan the sediment samples using microXRF and use the elementary maps to understand where and how different elements are located within the varve structure. So here again, we have the minerogenic lamina, and they are nice and easy. So titanium and silica are mostly related to the minerogenic matter. Oh, sorry. Yes, to the minerogenic matter. While iron can be, you can see it's here like in a particulate form, it can be related to the minerogenic matter, I think likely related to the heavy minerals that are quite frequently occurring at the catchment. And then it has like an amorphous phase. It's incorporated and precipitated in the organic layer, while the manganese is showing like faint strings in between of the layers. So yes, then we are back to the monitoring, and here this is Lake Kevojärvi. So it during spring floods, it has a really strong change of water level. It can change all the way up to 3-4 meters even during the spring flood, and then level up. But here you can see the spring flood and the summer stratification. So in this case, during the cold summer, it did not really stratify during the summer, but just waited for the winter to come, and then has this inverse stratification during winter. And then during more pronounced and more warm summer, it stratified again just before mixing, and it becomes anoxic during winter underneath the ice. And if the summer is warm, it becomes anoxic quite rapidly during the stratification. So the floods are nicely related to the minerogenic layers, yes, and the iron precipitation occurs during the growing season within the organic lamina, usually at the presence of oxygen. And manganese is easily dissolved in anoxic conditions, and I think this is very interesting because for the long record, we can see that some springs we do have manganese, like this thin manganese layer, but some parts of the records lack that. So I think there is much more to understand and investigate. And I think we are just, with regard of the biogenic layer, we still need to keep on working to better understand the construction and the biogeochemical processes influencing in biogenic lamina to actually be able to use it as a proxy for past. But I think it has a lot of potential anyway. So thank you for your interest. I'm looking forward to winter and ice cover to go back to the lakes and core some more sediments. Thanks.